Happy Thursday, you guys. I hope the test went well on Wednesday. Um, as a reminder, next week should be a normal week. We're heading into this. Today is the end of chapter 7. Next week, we're heading into chapter 6. We're going to be talking about areas and volumes and length. And we're going to do it in that order. But we really only have 2 weeks of lecture. So next week and the following week. And then you've got your final exams and you guys are done. So we are getting really close to the end here. A reminder that we are in right now section 7.7 on L'Hopital's rule. Right? And L'Hopital's rule was a simple way of doing a limit. So if I have limit as x goes to a of a function over another function, and if this has the indeterminate form 0 over 0 or infinity over infinity. So remember, if the top and bottom both go to 0 or the top and bottom both go to infinity, I can't tell immediately what it is. I have to do some more work. We call those indeterminate forms. So when that happens, what we can do is instead of looking at the limit of f over g, we look at the limit of the derivative of f over the derivative of g. When we do that, we put a little L apostrophe H over that equal sign that tells us we're using L'Hopital's rule. Okay? So we looked at some examples last time, like, let's do another really simple example. Limit as x goes to 2 of x squared minus 4 over x minus 2. Before, what we would do is factor the top, cancel the factor of x minus 2, etc. Now what we're going to do, if the top is going to 0 and the bottom is going to 0, then according to L'Hopital's rule, what we do is we just look at the derivative of the top over the derivative of the bottom and take that limit, and that limit is just 4. We're done. Okay. This is a really nice rule. You may need to do this multiple times. So we may need to do L'Hopital's rule multiple times. It's one of the things I pointed out last time. Another thing I pointed out is that this is not a substitute for the quotient rule. When we talk about this limit, we're not taking the derivative of the fraction, we're taking the limit of the fraction. And L'Hopital's rule says derivatives will help us take that limit, but the point is we're not taking the derivative of the fraction, we're taking the limit of the fraction. So don't confuse the quotient rule, when to use the quotient rule, with when to use L'Hopital's rule. So what I wanted to talk about today, I mentioned that we have these indeterminate forms 0 over 0 and infinity over infinity. But there are other indeterminate forms that I mentioned previously. So there's an indeterminate form connected to multiplication that is 0 times infinity. There's another one that has to do with subtraction that is infinity minus infinity. Do you remember us talking about this? And then there are some exponential or power indeterminate forms, 0 to the 0, 1 to the infinity, and infinity to the 0. The key behind doing these problems is we're going to try to turn the problem into either a 0 over 0 or an infinity over infinity problem. If we can do that, then we can apply L'Hopital's rule. Okay, we cannot apply L'Hopital's rule directly to these. You can only apply L'Hopital's rule in these very special cases. But if you can take one of these and turn it into a problem where L'Hopital's rule applies, then you're good to go and you can use L'Hopital's rule, okay? And for each of these, there's kind of a standard way to turn it from the form that it comes in into a form where L'Hopital's rule applies. So let's take a look at, let's do multiplication first. Okay? So for multiplication, we're going to be looking at things of the form 0 times infinity. Okay, so let's take a couple of examples here. Let's take the limit as x goes to infinity of x times e to the minus x. All right, this first term, when x goes to infinity, obviously the first term goes to infinity. E to the minus x looks like this. And when x goes to infinity, that thing is going to 0. So this is 0 times infinity. The idea behind this type of indeterminate form is if you can turn the multiplication into division, then typically you now have something you can use L'Hopital's rule on. So for example here, kind of a natural thing to do is this e to the minus x actually means that it's e to the x on the bottom, right? That negative exponent means it belongs on the bottom. What you'll notice now is that I do have a fraction, which is a great sign for L'Hopital's rule, and the top goes to infinity, and the bottom actually goes to infinity. So now I can actually apply L'Hopital's rule. I could not here, but I can apply it here. And what I'm going to do to apply L'Hopital's rule is I'm going to take the derivative of the top, which is 1, and the derivative of the bottom, that's my favorite function, e to the x. So now when x goes to infinity, the top goes to 1 and the bottom goes to infinity. 1 over a huge number, that is going to 0. Okay? So if I can turn this indeterminate form into an indeterminate form where I can use L'Hopital's rule, I'm golden. We can move forward from there. All right? Make sense? We'll look at 2 more examples. Okay, let's look at the limit as x goes to 0 from the right of x times cosecant x. Okay. Now, when x goes to 0, obviously the first term goes to 0, but unless you have cosecant memorized, you're probably thinking, I don't even know where that goes when x goes to 0. So what I would probably instinctively do is turn that into 1 over sine. Right? Cosecant is 1 over sine. Remember, they don't go together. Cosecant doesn't go with cosine. Cosecant goes with sine, and secant goes with cosine. Right? And this first term's again going to 0. Sine of x goes to 0 when x goes to 0. So 1 over 0, this is going to be infinite. It's actually going to be positive infinity. So you can see I've got a 0 times an infinite thing, and what I want to do, the recommendation that I made previously is you want to try to get it into a fraction form so that maybe you can apply L'Hopital's rule. Now you can see it's already kind of set up that way, right? So let's just turn that into a fraction. Let's just make that x over sine x. Okay, so now the top is going to 0 and the bottom is going to 0. So we're beautifully set up for L'Hopital's rule. The top goes to 1, derivative of x is 1, and the derivative of sine is cosine. And when x goes to 0, cosine of 0 is 1, so 1 over 1 is 1. Make sense? So this multiplication term, I want to get it into a fraction form. Now, obviously, these are fair. What I've shown you here works fairly well. It can get more complicated. So let's look at one example here. Let's try the limit as x goes to 0 from the right of x times the natural log of x. Okay. So x clearly goes to 0. Natural log, if you remember, looks like that. So when x goes to 0 from the right, the function shoots down to negative infinity. Okay. So we're in one of these 0 times an infinite thing realm, and I need to make a fraction out of this. So what I'm going to do, you're used to doing this the other way, But what I'm going to do is I'm going to take the x and flip it on the bottom and make it 1 over x. You're used to doing this the other way. You're used to taking a fraction in another fraction, and when it's in the denominator, flipping it up and making it x over 1, which would give you this. What we're doing is just the reverse of this, okay? So what we're doing is when I have an f times a g, what I'm doing here is I left g on the top and I made the bottom 1 over f, all right? If you did this in reverse and flipped this fraction, you would get f times g. The reason this benefits me is, again, the natural log is going to negative infinity, but the bottom now, 1 over x is going to 0, 1 over 0 is going to be infinite. So now I have a situation where I can actually apply L'Hopital's rule. Okay? So let's do that here. Okay, the derivative of a natural log is 1 over x. And the derivative of 1 over x, that's x to the minus 1, is minus x to the minus 2, right? So I just took the derivative of the top and the derivative of the bottom. The bottom is 1 over x, and so I took its derivative. All right. So now let's clean that up. So I've got 1 over x over negative 1 over x squared. Let's go ahead and flip that fraction now. So I'm going to flip it up and I'm going to get a negative x squared over 1. And now we can simplify that fraction some. I can cancel one of those x's. And I'm left with the limit as x goes to 0 from the right of negative x over 1. And when we let x go to 0, that's just 0. Okay. That makes sense? So what I did was I took one of these terms, put it on the bottom, and then I could apply L'Hopital's rule. And then I just cleaned it up using algebra, and the limit was something that I could then immediately do. Okay, so the key part right here is this transformation that I did so that I could apply L'Hopital's rule. And then everything else is just algebra trying to clean it up. Now, one immediate question you might have is, why did I choose to put x on the bottom? Should I have put natural log on the bottom instead? Because in the same way that I can put f on the bottom here, I could have left f on the top and stuck g on the bottom, right? It's whichever one of these I put on the bottom is not, it doesn't seem to have any preference one way or the other. Okay, so what I want to do with this problem is I want to show you what happens if I stick the other one on the bottom. It turns out it's bad. You wanted to stick the x on the bottom. I kind of helped you by making that choice for you. What I'm going to do is I'm going to show you what happens when you put natural log on the bottom. And then I'll talk about how do you know which one to put on the bottom, because one of them tends to be better than the other one. Okay? So let's try that same problem. So x times the natural log of x. But what I'm going to do is I'm going to put the natural log on the bottom. All right? So I'm going to leave the x on the top. And I'm going to make it 1 over the natural log of x on the bottom. So now the top is going to 0. Natural log is becoming infinite when x goes to 0. 1 over that is, 1 over a huge number is a really small number. So the top and the bottom here are both going to 0 now. So I can do L'Hopital's rule. Okay. And the derivative of the top, let me just section this off. The derivative of the top is nice. Derivative of x is just 1. Okay. But do you see what's going to happen on the bottom? So this is natural log of x to the negative 1. So what I'm going to have down here is negative natural log of x to the negative 2 times the derivative of the inside is 1 over x. If I clean that up, I've got a negative. Natural log of x to the negative 2 means it belongs upstairs squared. And the 1 over x belongs upstairs flipped, so that's just x. Compare. Did you see what I did? I took natural log of x, since it's to the minus 2, I stuck it upstairs. And the 1 over x I stuck back up as x. If you compare this fraction, sorry, this one with this starting one, my marker isn't working here. If you compare these two things, notice that the limit actually got worse. Before I had an x times natural log, now I have an x times 2 natural logs. That's worse. So generally when you put one of them on the bottom, the fraction will get better. See, this is a much better fraction. The other one on the bottom ends up making the fraction worse. So you might ask, well, how do I know which one to put on the bottom? Well, the rule of thumb is that if you're choosing between an e to the x, an x, or a polynomial, and a natural log, the e to the x goes on the bottom really easily. Like if I have e to the minus x, it goes downstairs very easily. So you want to pick the e to the x first. That makes you happiest. The next choice, if you're comparing things like x versus natural log, if I don't have an e to the x, if I have just x and natural log, you want to pick the polynomial. That's okay. It's not that great, right? This was kind of, when I stuck it on the bottom, it wasn't beautiful, but at least it gave me an answer. You almost never ever want to stick natural log on the bottom. Natural log on the bottom is just a recipe for disaster. Okay? So generally when you're having to make that choice between product of two things, stick the e to the x on the bottom first if you can. If you can't, and you're comparing like an x and a natural log, stick the x on the bottom. Do not ever put natural log on the bottom. Okay? So again, the idea is if I have a multiplicative indeterminate form like 0 times infinity, you're trying to turn it into something that I can do L'Hopital's rule on. Okay. So that was the first one that we were doing. Let's look at, the next one's actually easier. The next one we're going to look at involves subtraction. So the subtraction indeterminate form is infinity minus infinity. Okay, so the subtraction indeterminate form is infinity minus infinity. And so let's look at two examples here. Let's first look at the limit as x goes to 0 from the right of 1 over x minus 1 over sine x. Okay? So when x goes to 0, 1 over 0, this is going to be infinite. And sine of x also goes to 0, 1 over that is infinite. So I have infinity minus infinity. The thing that we always try to do here is we try to get one fraction or a common denominator. Okay, so here we're trying to get one fraction, we're trying to get a common denominator. So in this case, my common denominator is going to be x times the sine of x. It's going to be the product of those two things. And what I'm missing in the first part is a sine x. So sine x over x sine x gives me 1 over x. And what I'm missing in the second part is an x. X over x sine x gives me 1 over sine x. Okay? So that's my common denominator, and that gives me my fraction. So now what you'll notice, if I let x go to 0 after getting a common denominator, the top goes to 0 and the bottom goes to 0. So now I live in a space where I can do L'Hopital's rule. So let's try that here. So what we're going to do is the derivative of the top, so I get derivative of sine is cosine minus 1. And the bottom is a product, so here I do have to use the product rule. Okay? I need the derivative of the bottom. The bottom's a product, so what I'm going to do is derivative of the first times the second plus the first times the derivative of the second. Okay? So now when I let x go to 0, cosine of 0 is 1. 1 minus 1 is 0. The top goes to 0, and the bottom, sine of 0 is 0, and 0 times 1 is 0, so the bottom still goes to 0. So I am now going to do L'Hopital's rule again. All right, and the derivative of cosine is negative sine. The derivative of 1 is 0. Derivative of sine is cosine. And now for x cosine x, I have to do the product rule, so I'm going to do derivative of the first times the second plus the first times the derivative of the second. Okay. So now when x goes to 0, sine of 0 is 0, the top's going to 0, but notice that the bottom is going to 1 plus 1 plus 0, so the bottom is going to 2. So before you get to L'Hopital happy, you're actually done. 0 over 2 is 0. Okay, so that limit turns out to be 0. All right? Okay, let's look at one more example. Let's do the limit as x goes to 0 of cosecant x minus cotangent x. Okay. Now, when you try to plug in 0, you might get confused about what is cosecant and cotangent, what in the world are they doing. So the first thing that I would probably do is turn these into sines and cosines. Cosecant is 1 over sine, and cotangent is cosine over sine. So when x goes to 0 now, 1 over 0, this is going to be infinite, and cosine of x is 1. 1 over 0 is also going to be infinite. So that tells me that I've got one of these subtraction indeterminate forms. So let's get a common denominator, which in this case is super clear. Our common denominator is sine. And on the top I have 1 minus cosine. And what you'll see now is that when x goes to 0, the top, 1 minus 1, the top goes to 0 and the bottom goes to 0. So again, I'm set up in a perfect situation to do L'Hopital's rule. So I'm going to have the limit as x goes to 0. Derivative of the top, derivative of 1 is 0. Derivative of negative cosine is negative. Derivative of cosine is negative sine. Derivative of sine is cosine. So let me clean this up just for a second. So this is limit as x goes to 0 of sine over cosine. So now, when x goes to 0, the top goes to 0, but the bottom goes to 1. So my overall limit is 0 over 1, which is 0. Okay? So the key to these subtraction types of indeterminate forms is we get a common denominator. And again, the point is to get to a place where I can use L'Hopital's rule. If I can use L'Hopital's rule, I'm golden. All right. Okay. Last category of indeterminate forms, and these are our power indeterminate forms, okay? So our power indeterminate forms are 0 to the 0, 1 to the infinity, and infinity to the 0. The overall way that we're going to do this, so what's happening here is we're looking at the limit as x goes to a of some function to the power of some other function. Okay. What we're going to do here, the overall strategy, because this is a very different kind of problem than anything that we've done previously. The overall strategy that we're going to do here is that rather than looking at this limit, which we can't do right away, what we're going to do, we're going to call this function f to the g, we're going to call it y, and we're going to look, instead of looking at the limit of y, we're going to look at the limit of natural log of y. And the reason that we're going to do that, natural log has this really nice property that I can take powers. Remember this? I can take powers and pull them out front. We actually used the natural log when we were doing something called logarithmic differentiation. When we had power to a power and we wanted to pull that power out front, we use natural logs. We're going to do the same thing here. So we're going to have that g function come out front of the natural log. And instead of looking at this limit, we're going to look at this limit. And what's going to happen is this limit is going to end up having the form 0 times infinity. So then we're going to put one of them on the bottom, and we're going to then be able to do L'Hopital's rule. Okay? So applying natural log and looking at this limit will eventually get us to a place where we can get a number here. Okay? Once we have that limit, then the way that we're going to get the original limit is we're going to use a little trick that y is equal to e to the natural log of y. Right? Y equals e to the natural log of y. E and natural log cancel. So if natural log of y is going to some number, then y is going to e to that number. Okay, so in other words, if I did this fraction, if I did this limit and the limit ended up being 1, then the original limit would end up being e to the 1. Okay? You'll see what I mean when we do a few problems. We'll do about 3 examples of this, just so you can get it under your belt. Okay? All right. So let's first look at the limit as x goes to 0 of x to the x. Okay? So this is one of our indeterminate power forms. I've got a form 0 to the 0. 0 to any power should be 0, but anything to the 0 should be 1. So these, again, battle each other. So what we're going to do is we're going to let y equal this function, and we're going to take the natural log and pull this power out front. Okay? So I let y equal x to the x, and I take natural log of both sides, and I can pull that power out front. So I'm looking at x, natural log x. So now, instead of looking at the limit of y, in other words, x to the x, I'm going to look at a totally different limit. I'm going to look at this limit, natural log y, which is x, natural log x. Okay? So we're going to ignore this problem. We're going to put this problem on pause for a second and look at a very different problem. Now, this was a problem we did previously. Do you remember which one I put on the bottom? So this thing goes to 0 and this thing goes to negative infinity. So this has a product indeterminate form, which meant I needed to put one of these on the bottom. Do you remember which one I put on the bottom? I put the x on the bottom and made it 1 over x, so that the top is now infinite and the bottom is infinite. And then we did L'Hopital's rule. Okay? I'm going to spare you the details here. I could take the derivative of the top, the derivative of the bottom. You can look back at your notes. But this limit ended up being 0. okay? So just trust me, that limit ends up being 0. So natural log of y, in other words, this thing, natural log of y, is going to 0. So then if we backtrack and ask, where is this function going? Well, y equals e to the natural log of y. And if this thing is going to 0, then y is going to e to the 0. In other words, the overall limit is 1. Okay? Make sense? We'll do a couple more examples of this so you can kind of get the hang of it, but hopefully this kind of makes a little bit of sense. All right. Okay, let's try another example here. Let's do a different one. We're going to do a 1 to the infinity type. Okay. All right, let's do the limit as x goes to infinity of 1 plus 5 over x to the x. Okay. So 1 plus 5 over x to the x, and x is going to infinity. So notice that the inside goes to 1, and the power goes to infinity, so I have a 1 to the infinity type. 1 to any power should be 1, but any number to the infinity should end up, any number bigger than 1 to the infinity should end up getting big. So these, again, fight with each other. So what I'm going to do is I'm going to let y equal this complicated thing. And in order to take that power down, I'm going to take the natural log of both sides. Okay, so natural log of 1 plus 5 over x, all to the x. Let's pull out that power. So we get x natural log of 1 plus 5 over x. Okay. So now instead of looking at my original limit, in other words, the limit of y, I'm going to look at the limit of natural log of y. Okay, so I'm going to look at the limit of this thing, x times the natural log of 1 plus 5 over x. Okay. Now what you'll notice is the first term's going to infinity, and the second term, 1 plus 5 over x goes to 0, this goes to 1, the natural log of 1 is 0. So we're into our 0 times infinity situation, and one of those needs to go on the bottom. Which one? The x or the natural log of 1 plus 5 over x? Which one goes on the bottom? And if you said natural log of 1 plus 5 over x, I will climb through the camera and find you. Okay? No, but seriously, this is terrible. Please do not put that on the bottom. Okay? So what we're going to do is put the x on the bottom to make it 1 over x. And again, remembering that if I flip that back up, I would get that original thing. So now the top is going to the natural log of 1, which is 0, and the bottom is 1 over infinity. That's also going to be 0. So now I can do L'Hopital's rule. So let's do that. All right, so the derivative of the top, I'm going to have to use the chain rule. So I've got the derivative of natural log is 1 over x. So then I plug in my function. Times the derivative of the inside. Well, the derivative of 1 is 0. And the derivative of 5 over x is negative 5 over x squared. Make it x to the negative 1 if you're not sure. Okay. So that's my derivative of the top. The derivative of the bottom is, the derivative of 1 over x is negative 1 over x squared. So what you can actually see, if I do some cancellation here, these negatives cancel, and the x squareds on the bottom of each of those fractions cancel. So things actually work out fairly nicely. I've got the limit as x goes to infinity of the top becomes 5 over 1 plus 5 over x, and the bottom's just 1. Everybody follow? So now when x goes to infinity, the top is just 5, and the bottom is just 1 plus 0, so that is overall 5. The danger with these problems is that you've done all this work, you've worked really hard, and you end up getting to an answer. Many times people forget that you have to then turn around. You didn't solve the original problem, you changed the original problem and solved that. So you have to be sure to go back at the end and remember that the original problem was e to this thing. So you have to make sure that you take e to your final answer. The final answer is actually e to the 5, not 5. Because you figured out where natural log of y is going, but you still need to figure out where y is going. So you have to take e to that last answer. Many times students forget that. Okay? So don't do all this work and then circle that answer without taking e to it. That's something that's super, super important. Okay? Make sense? All right, we'll do one more example here, and we will be done, and you'll have some time to work on some of these L'Hopital's rule problems for your homework. And these will be due on Monday. So just one more example here. Okay, let's do the limit as x goes to 0 from the right of e to the x plus x to the 1 over x. Okay. Now when x goes to 0, so again it's e to the x plus x to the power 1 over x. When x goes to 0, e to the 0 is 1 plus 0. This goes to 1. And 1 over 0 is infinite. So we are, again, in this case of a 1 to the infinity situation. So what I'm going to do is I'm going to let y equal this function, e to the x plus x to the 1 over x. And I'm going to take the natural log of both sides and consider that function instead. Okay, and again, the nice part is that that power comes out. So I get 1 over x times the natural log of e to the x plus x. And instead of looking at this original limit, the limit of y, I'm going to look at the limit of the natural log of y. So the limit of 1 over x times the natural log of e to the x plus x. Okay? Everybody follow so far? Now, in looking at that limit, when x goes to 0, 1 over x goes to infinity. E to the x goes to, e to the 0 is 1 plus 0 is 1. The natural log of 1 is 0. So again, I get a 0 times infinity situation. I want to put one of these on the bottom. I need to make a fraction, and there's a natural way to make a fraction. I've already kind of have a fraction here, right? So let's do that. So let's change this into a fraction. So we're going to do the natural log of e to the x plus x all over just x there, right? And now the top goes to 0 and the bottom goes to 0. So I am in a perfect place to do L'Hopital's rule. Okay. Let me let you do the derivative of the top and the derivative of the bottom. Take a second and do that here. Okay. Let me just give you a minute and let you do the derivative of the top and the derivative of the bottom and see what you get. Once you think you have an answer, compare with your neighbor. Okay, the derivative of the bottom is the easy one. That's just 1. So we can take care of that. Derivative of the top, I have to use a chain rule, so I get 1 over x, then plug in the bottom. We'll plug in the inner function, e to the x plus x. And then I have to multiply by the derivative of the inner function, which is e to the x plus 1. Okay. So in other words, cleaning this up, I have the limit as x goes to 0 from the right of the fraction e to the x plus 1 over e to the x plus x, and the bottom is just 1. So now when I let x go to 0, the top is 1 plus 1. The bottom is 1 plus 0. So the limit should be 2. Am I done? No, we need to make sure that we go back. We've solved this problem, but we haven't solved this problem. So what is that limit? The overall limit then is e to the 2. You have to take e to that last number because, again, we're trying to solve y, but y is the e to the natural log of y, and we figured out where natural log of y is going. So if that's going to 2, y is going to e to the 2. Okay, that's a critical last step in these problems. All right, so you've got, I think, only one of these on the actual homework, but I wanted to give you some chance to experiment with a few of these just to try them out. So give those a try. You should have some time in class today to work on those, and we will see you all on Monday. Take care.